Welcome everyone. Today's discussion will be about programming AMCI Ethernet IP stepper controllers using the Studio 5000 and RSLogix 500 softwares from Rockwell Automation. We have a lot to cover today, so let's get started. For today's discussion, we have a few topics to discover. The first is what products are covered. AMCI manufactures a lot of different stepper controllers for the Allen Bradley PLCs, plug-in cards, and devices that communicate via the industrial networks. The products we're going to be discussing today specifically cover those products that communicate to the PLC using the EtherNet IP protocol. We're going to touch upon the input and output data structure, specifically what data we are sending to and what data we are receiving from the particular devices. We're going to look at how to use these devices in RSLogix 500, which will cover off on the MicroLogix product families, as well as the SLIC 500 product family. In this particular programming environment, we're going to be using what are called message instructions. Then we will go into a discussion about the RSLogix 500 and RSLogix 5000 and Studio 5000 programming environment for the ControlLogix and CompactLogix PLCs. And then we're going to round out the discussion by looking at what's new from AMCI relative to the programming structures of RSLogix 5000 and Studio 5000. And then close it out with a discussion and Q&A section for those that would have questions about the programming or using any of these devices in the Allen Bradley environment. As I said, we make a lot of different products for the Allen Bradley PLCs. Today's discussion is going to wrap around those products that communicate via Ethernet IP. Specifically, we're talking about the SD17060E stepper drive and controller, which is an AC powered stepper drive. We're going to be looking at the ANG1E, which is a DC powered stepper drive controller. And we're also, when we're talking about controller and or devices, which are words that can be used interchangeably throughout the discussion, we're also referring to the SMDE and SMDE2 products that communicate to the PLCs. These products are stepper motor drive, control, and motor all in one package. Before we get started, we're going to have to make some assumptions. The first is that you or the user is familiar with ladder logic programming. They don't have to have a very deep knowledge, but when I talk about adding a component or conditioning a rung, they should have some basic understanding what I'm referring to. The user should know how to add a device to a network in RSLogix Studio 5000. We'll look at that, how that's done, but I'm not going to go into the breaking it down to its most basic level because you should know how to do that or at least have had some experience doing so. And then you should also understand how the data is stored in your respective program. Whether we're talking about RSLogix 500, when we're doing that, we're talking about using the integer files. And when we're talking about Studio 5000, we're talking about using data tags. Relative to the AMCI components, what you should know is how to set the IP address for your controller. All AMCI devices leave here with an IP address of 192.168.0.50. You may have a situation where the controller you're connecting to is of a different network, so you need to change the IP address. You should know how to do so. There's a lot of tools available, boot P servers, AMCI net configurator, to name a few. You should know how to do that and how to make that happen. You should also know that configuration and motion commands are sent as data blocks. And that's really what we're talking about today is those data blocks and how they're manipulated within the programming environment. And you should also know that in general, move commands are not stored in the controller. And really what we're talking about here is once I've executed a move, the device needs to receive another command for the next move. We're typically not going to store a series of commands and then just trigger them through an input. That's not how these devices work. They're designed to communicate directly with the PLC and receive commands from the PLC directly. Okay, so the first data block we're going to look at is the configuration data block. When we're talking about configuration data, we're talking about the information that defines the controller setup. The data that we send when we send the configuration block, we're talking about setting up the steps per turn. A typical stepper motor is a 200 step per turn motor. By using micro stepping, we can take that 200 steps and break that up into finer and finer increments. This is where in the controller we define that steps per turn or that micro stepping feature. We define the starting speed, which as is the starting speed. It's the initial rate at which the device starts moving the motor. In this particular case, we define the starting speed in steps per second. You also define the current. When we define the current, we're defining the running current of the motor and also the idle current of the motor. The idle current is a feature where, as when the motor is at rest, the controller can reduce the amount of current going to the motor, which helps reduce motor heating, save energy, and extend motor life. If you're using an encoder for your system, whether it's an external encoder like you would use with an SD17060E or the ANG1E, or if it's an internal encoder like you would use with the SD17060E, the SMD23E or the SMD23E2, those would be defined here in the encoder pulses per turn. And then these devices have external inputs. Those external inputs have many functions, and this is where you can define those inputs, whether it's a end limit function, a homing function, so on. You would define that here, and you would also define the active state of that input, whether it's active high or active low. And the most important feature of the configuration block is the configuration bit. This is the configuration bit. It's the last bit, or bit 15, in the very first word of the data block that we send down. If this bit is not set, the device or the controller does not recognize it as configuration data, and it will either be ignored or you will generate an error because you're sending down information which doesn't coincide with what the controller is expecting. Any questions on that? Okay, I have a question here about motor current. The motor current is something that you're going to get from the motor supplier. Typically, the motor will be rated with a maximum current. This is the value, the maximum value that you enter here. So, for example, if your motor supplied has a maximum current rating of 3 amps, you would put 3 here. You don't necessarily need to push 3 amps through the motor, but that would be the maximum value that you would want to enter in here under your motor current. Okay, the next data block that we're going to send is the command data. This is really where the rubber meets the road. This is where we're defining the motion that we're doing with the controller. When we send command data, we're going to send a move type. That move type will define whether it's a absolute move, a relative move, jog move, home command. All that's done here under that part there, that portion there that's defined as move bits. And when you're sending a move command, you can only set one move bit at a time. If you set more than one move bit, you will generate an error. You also set the velocity value, which is defined in steps per turn, or steps per second, and also the distance. So for example, if we're doing a relative move, this is the number of steps that the move will execute, or with an absolute move, it'll be the position value that the motor will be moving to. And lastly, we will set the acceleration and deceleration rates of the move profile. Everything that would be defined here in this command data block. And with the command data block, that bit 15 needs to be a 0. If it's a 1, it's going to think it's configuration data, and you'll probably set yourself a configuration error bit because the data that you're sending is not what it would expect as configuration data. Any questions here? Okay. Now that we've seen what we're sending to the device, what kind of information are we getting back from the device? We're going to be getting back quite a bit of status data when we read from the controller. That status data will include controller status. The controller status will say, is everything okay with the hardware? Do we have any errors, such as a configuration error or a command error if I gave it a bad command move? And it also will give back what we call the heartbeat bit. The heartbeat bit basically just toggles on and off once per second so that when you look at your status data, you can see whether or not the device is communicating with your controller. We're also going to send move status bits back to you. That move status will include a clockwise moving bit or a counterclockwise moving bit, acceleration, decelerating, or if the axis is stopped, and or if that move that I just executed has completed. And that's very important information for us that we'll see later on. It will report back motor position. So when I've commanded it to go or when it's moving, you will see this motor position being reported back to the controller, to the PLC. If we're using an encoder, the encoder position will be reported. And it's also going to tell us what our programmed current is. It's not the running current of the motor, it's the programmed current of the motor. Any questions on this information? Okay, I have a question here, and it's about the data structure of the position and what is upperward and lowerward. In all of our devices, whether we're talking about these Ethernet IP devices or even our PLC modules, we break up the large values, which could be the motor position, velocity commands, numbers that are greater than, say, 32,000 need to be broken up into 2 words because we're looking at a 16-bit data word when we're transferring it over. So for those ones that are larger than 32,000, we came up with this method of sending over data. And that method is breaking it up into what we call upperward and lowerward. In the lower word, we're transferring the value which would contain the 1s, 10s, and 100s position, and the upper word contains thousands, 10,000s, 100,000s. So for example, if the motor position is, say, 550, my motor position value would be 0 in the upper word and 550 in the lower word. If my motor position is, for example, 11,550, I would have 11 in the upper word and 550 in the lower word. Kind of giving you an idea of exactly how we break that up. Okay. All right, now jumping into the actual programming, we're going to start by looking at the RSLogix 500 programming environment. To do this in the programming environment within RSLogix 500, we first have to start by adding a message instruction as a rung element and then entering the setup screen. As I said earlier, you should have some basic understanding of how to do that. And when you've done that, the screen that you see here on the right-hand side of the page is what will appear. And from here is where you will enter all of your setup data. And that setup data can be found in the controller manual. Not only do you enter in the setup data, such as the number of bytes that I'm sending back or reading from the device, but also the assembly instance. And also, I'm going to set up where I'm either reading the data from within my integer files or where I'm sending the data to in my integer files of that particular message. Once I've done that, I click on the multi-hop tab, which is where I will enter my IP address. And when I've done that, the following screen will appear. I simply enter in the IP address of the device. In this case, we're using the AMCI default value. Once that's, you click on OK, and you've completed the message setup for the AMCI controller. And when we're done, we should have 2 message instructions, a write instruction and a read instruction. The read instruction will read the status information from the controller, and the write instruction will send the information to the controller. Okay, once I have all of my messages set up and everything is communicating correctly, to execute a move or to send a configuration file is simple. We simply create a ladder logic rung with a particular set of conditions which works for what we're trying to accomplish. And then at the end of that rung, we have a copy instruction. And we take that, and within that copy instruction, for example, with a message write or a move command, that copy instruction will contain the move data block, and we'll send it to the integer file, which we set up as the write instruction integer file. And for this particular function, the logic is conditioned such that only one command can be sent at a time. If we try to send 2 commands at once, we will get a command error. Assuming we've done everything correctly, we should now have motion on our device. Okay, so what does that data look like when we're looking at the integer files for the RSLogix 500? Well, it looks like basically what you would expect here in the integer file. This first data block that we're going to look at here, this is what it would look like, a typical configuration file would look like in your integer format. The very first word, which is word 0 here, or excuse me, word 10, that contains our configuration setup word, which is where we're defining the inputs and setting that configuration bit. And as we move along there, we can see that we have a program starting speed of 100, a typical steps per turn of 400, idle current, motor current, so on and so forth. That's what typical configuration data would look like. And then the rest of the data that we're looking at here are pretty much command data. This particular command here, we're going to be executing a relative move. And as you can see here, we only have 1 bit set in that command word, because when we're sending a command, we can only set 1 bit at a time. And then we follow that up with a velocity value, a position value, an accel and decel value. And you can see it's a very similar setup for all those commands. We're setting that 1 bit depending upon the command, whether it's a jog, a clear error command, a preset position command. They all have a very similar data structure as you would expect. Any questions on that? Okay. Okay, looking at Studio 5000 or RSLogix 5000, but here we're going to reference it as Studio 5000 for both of them. When we're creating or adding a device to a network there, we add the device under the new module for a network. So we open up our network tab here on the left-hand side of our programming screen and click on new module. Once I've done that and clicked on new module, I get the setup screen here, and I select the generic Ethernet module type, and then I would enter in all of my network setup data, which would be found in the user's manual, just like it was with the RSLogix 500 programming environment. One thing of note here that I would point out when adding a device to the RSLogix 5000 or Studio 5000 is this communication format value. Definitely needs to be data integer. Most of the tech support calls that we've gotten over the years for people having issues setting up is they forget to set that to data int. The default format when adding a generic module is data dint, and it doesn't work in that fashion. It sends data in an integer format. If you set it as data dint, you'll get an error and it won't communicate correctly, and you'll have to start over again. Once you entered in all the setup data and click OK, you now have created data tags within the RSLogix environment. As you can see here in the upper top, we have created config files, input and output registers. These are the registers that we'll be using when programming in the Studio 5000 environment for both sending information to, which is going to be the output registers, or reading data from the controller, which are the input registers. Okay, now in this environment, we're not using messages. We're using simply copy instructions. And that process is going to be the same process whether we're sending command data or configuration data. We have a series of instructions here on the left-hand side of our rung, which condition the logic such that when that rung is true, we send this copy command. In this case, we're sending a relative move. And we're sending that relative move from a tag file and copying it over to the output registers of the controller. One thing of note is a move occurs when a command bit transitions from 0 to 1 in that command word. So what will happen is when we send that command, it sees the information and we execute a move file. If for some reason we have a motion command set and we don't clear out that very first word and we try to send another command, it cannot execute on it because that bit that's already there in the command word is still on, so we have to clear that out. So typically what we will do is we'll use some of those status bits that we talked about earlier, such as axis is moving, and when the axis is moving, we simply move a 0 over to command word 0, clear that register so it's ready to move the next motion command. Any questions here? Okay. So you've seen how we've done the programming, and we do everything with copy instructions. One of the things that we've had a lot of questions about in the past were add-on instructions. Add-on instructions are for people who are familiar with the Allen Bradley programming environment in Studio 5000. It's basically a subroutine that is created by the manufacturer, which allows you to simplify your programming. Basically, the subroutine acts in the background. The programmer doesn't see it. And when they want to add an instruction, they would simply go down to that tab where they would say, which includes the add-on instructions, and select, say, AMCI SMD 23E absolute move command. And instead of entering a copy instruction and a series of logics to execute that absolute move, they simply enter in this function block. And as you can see here, it provides a more intuitive programming structure. So instead of having just data tags with numbered 0 through 9, you can enter in a value here that shows up as target position. I know exactly what I need to enter there, put my target position in, program speed, XL, decel, so on and so forth. It also helps eliminate the old cut and paste method. Oftentimes, if we're doing logic and we have a series of logic to execute a move or a particular command and we need to do it over and over again, we'll cut and paste, which can sometimes lead to sloppy code because we're leaving in bits that aren't necessarily needed for that particular section of logic. The add-on instructions help eliminate that. When we're setting up the add-on instructions, the variables can be either numeric entries, as we have here, or you can use tag-based entry, which would allow you to use things like your HMI to make changes directly to these values. And it also will provide consistency between programs. So the logic that I do for one particular setup, and next time I do my next machine or my next build, it's the same exact logic because it's all contained within that add-on instruction. Any questions there? Okay, and if anybody's interested in using or taking a look at the add-on instructions, they're available at our website, www.amci.com. Okay, and closing things out here, the other thing that we've heard a lot of questions about, people looking for add-on profiles. These network devices don't come with add-on profiles, but we are developing an EDS file, which if you've done any networking in the past, you're familiar with. The EDS files are going to allow us some seamless integration into the PLC, because once you've added the AMCI controller EDS file to your Rockwell software, when you go to add a device, instead of adding it as a generic device, it will show up underneath the vendor's filter for the module type. In this case, we've selected out only the AMCI to make it a little bit clearer what you're looking at. So the product would show up there, and we would select the product type, in this case, the SMD 23E2, click on that. And now my setup is also a lot easier. I no longer have to open up a manual, look at my assembly instances, the number of words going back and forth, my data type. All I need to do is enter an IP address, and I'm ready to rock and roll. And the other thing we're going to be doing in the EDS files is we're going to be taking advantage of the controller's configuration tags. If you remember in the generic setup, we weren't using those configuration tags. We were only using input-output registers. What we're going to be doing here is using these config tags, which will allow you to have a default configuration set up within your logic. You would use this to do your config data, and then you would only be using the output registers for doing command data. That would be its own function, and entering configuration data would be its own function under these config tags. And by using the config tags, it allows us to break up that configuration data to a little bit more intuitive. So when I open up the logic underneath that particular tab, I can see exactly what each bit and what each word means instead of having them just numbers 0 through 9. So it's a very nice feature. Any questions on that? Okay. All right, that concludes our presentation today. If anyone has any questions, I'll be happy to field them at this time. Please feel free to take advantage of the chat window to submit any questions you may have. All right, seeing as we have no questions, I'd like to thank everybody for their time today. I know our presentation was a little longer than typical, but I think the information that you received was worth it. Thank you, everyone, and have a safe and fun weekend.
Thanks, Matt.
Thanks, Matt.
Good job, Matt.
Thank you, Matt.
Thanks, Matt.